Here we are in homework 19, problem 1, where we have this friction problem where we have these two blocks. This one is 50 kilograms. It's at a 20 degree slope right here. We have a static coefficient of 0.3. And, you know, one issue of this is I have to make sure that this thing can actually slide, now that I'm thinking about it. I'm a little nervous that 20 degrees wasn't enough for this thing to actually slide. That could have been a big mistake. Well, yeah, because 20 degrees isn't a whole lot. In fact, I think I might be able to do that right here at the top of my head. And 0.3 might be too much. So if you take the inverse tan of 0.3, okay, that's 16.69 degrees. Okay, so it will, I believe it will slide. We'll see that coming up here in a bit. So anyway, okay, so this is 10 degrees. We want to find the range at which this is required, or the mass of this required to keep it from sliding. Right, there's a sort of a minimum and a maximum that can be done. All right, so I've written this thing out, and I start out with an FBD. I'll start it off with the FBD of this guy. Make him look reasonably blockish. We'll put in. We're going to cut the cables right there. And it's got a weight coming downwards, like right there. And here is the slope of the thing. We'll call this an FBD, and we're going to make the coordinate axis aligned with the slope. And I like to call them X prime and Y prime right here. And then we have a normal force, and we have a friction force. Now the friction force, it can be drawn in either direction here. And by that I mean, this tension might not be enough so that it wants to move down, right? So maybe I'll write this as the sliding down FBD. And then I'd write over here the sliding up FBD. Right? And so in this one, if it's going to slide downwards, then the friction force is in this direction. Let me put these other things in here. Here's N. And I might call this A and this A right in there. And here's weight of A, and here's my angle of theta. Right. So here is the same FBD. Maybe it's better to have this, separate these out instead of trying to use the same FBD for both of them. Right. So here we go. Here's the weight, and then here is. So we put the arrowhead on the weight better. Weight A, F N A, F T, and here's theta, and here is my friction force. But in this case, it's going to be coming this right here. Right, so now it's trying to slide up because this thing weighs so much. It's pulling it, going downwards, which is pulling this up right in there. So there's my FFA right in here. Okay, so what we do first is we go the sum of the forces in the y prime direction is equal to 0, setting it up this way right here, and we say WA downwards, which is going to be mass of A times gravity, times the cosine of theta right there, plus 2 times Ft right here. Nope, I'm sorry. I don't know what I'm saying right here. Plus Fna equals 0 right there, right? So Fna is equal to mass of this, which is 50, times 9.81 times the cosine of 20 degrees. Or, let me see here, that would be 50, 9.81 times, and then, I say 20 degrees, 20 cosine, and then times. All right, so that's going to be 460.9 newtons. So my FFA is going to be equal to mu times FNA, or coefficient of friction of 0.3 times 460.9, and that's 138.3 newtons. And then this is actually going to be the same thing for over here. Nothing over there changed. So we take the sum of the forces in the x prime direction. See, let's be aligned with this right here. In the x prime direction equals 0. X prime is going up the slope that way right here. And we're going to say, once again, that's going to be a negative MAG, but now the sine of theta. But up the slope, we're going to have a plus FFA, and then a plus 2FT equals 0. And I better hope this works out the right way right here. So I'm going to have a negative 50 times 9.81 times the sine of 20 plus 138.3 plus 2ft equals 0. And I'm going to have ft equal to, it better be something good here. Let's see, 50 times 9.81 times and 20 sine times, ooh, we were lucky. This is bigger than that, okay? So we can subtract it out and divide by 2, and we get that cable tension needs to be 14.74 newtons for this thing not to slide down, right? That's the break-even point when this thing starts to slide. But if we do this over here, we go to the sum of the forces in the x prime direction equals 0. And now notice everything's going to be the same except for the sign of this friction right here, right? So we're going to say that we're going to have a negative MAG sine of theta, but now minus FFA plus 2FT equals 0. So now we have minus 59.81 sine of 20 minus 138.3 and then plus 2ft equals 0. So ft in that case is going to be 1 times 20 sine times same thing, but now we have to have 138.3. We add them together and divide by 2. So now this is 153.0 newtons is the tension required to keep it from sliding down. So we go to a second page here. And I guess I should not have circled that if I was going to be consistent here. I don't usually circle. Just continued here. We take the other FBD, right? So this other guy right here, drawn FBD on him, he's much steeper slope. and he's just being pulled up right here. So here's an FBD, and I am going to make this the, doesn't really matter, I guess. It does kind of matter. Yeah, it does matter. Here's going to be my y prime prime, my x prime prime. They're different ones, double prime, whatever. And then we can have the normal force right here, F and B. Now here's the important part here. We have the weight of B. And I'm trying to figure out a place to put the angle right here. So put it right there. Beta. So the sum of the forces in the x double prime direction has to equal 0. We don't really care about what happens in the y direction, the y double prime direction. So we look at this and we say, okay, well, I need ft. So negative ft and then in the plus WB, which is actually MBG, but that's going to be the cosine of beta equals 0. So ft is equal to MBG cosine of beta, or MB is equal to ft over g cosine of beta. All right, say so for block A sliding down, or to prevent it from sliding down, MB is equal to 14.74 divided by 9.81. Notice that the 9.81s would eventually have canceled out anyway. That's right. And then we have the cosine of 10 degrees. So let's see. 14. Well, actually, it might still be in the calculator. Yeah, it is. There you go. So 9.81 divided 10 cosine divided, and all it has to be is 1.526 kilograms for block A sliding up, or actually to prevent it from sliding up. MB is equal to, what did I say here? 153. Yeah, 153. 9.81. And then the cosine of 10 degrees. So, yeah, so 9.81 divided 10 cosine degrees divided, and we get that it's got to be 150. No, 15? Is that all? All right, that's not much, right? Yeah, okay. 15.84 kilograms. So the answer (1.53 kilograms). MB 15.8 kilograms. Did I say that right? MB must be less than this, but greater than that. Yes. Okay. Ta-da! Done. How fast? How fast? How fast? 15 minutes. Oh, I gotta go to bed. It's like 12. No, it's 11:50 at night.